Now that we've seen all the major forces for this course, we will examine what happens when the forces are not pointed exactly along the x or y axes. That is, if they are pointed at oblique angles. The solution is similar to what we did in kinematics. We treat such forces as being in polar notation and convert them into rectangular using the sine and cosine of the angles, thus breaking the forces into their x and y components. Here's an example. A 20-kilogram asteroid is tethered to two ropes. The tension in each rope is 50 newtons. The ropes are oriented 60 degrees apart. What is the overall acceleration of the asteroid? In this question, we've been told that there is a 20-kilogram asteroid which is hooked up to two tethers. One pointed this way and one pointed this way. Or at least we'll visualize it like this. Each tether is providing a tension of 50 newtons, and the angle between them is 60 degrees. Now let's draw the free body diagram of the asteroid. We represent the asteroid, as always, as a spot. T1 points in the rightward direction, and T2 points at this oblique angle, 60 degrees above that. The question that you're going to run into whenever you have oblique angles is, which way do you set your axes? In this case, it's pretty straightforward. You always set the origin at the spot in the free body diagram, and you always set your axes so that one of the forces is lying along the axis. There's a reason for doing that, and I'll show you why in just a second. Let's say that we want to have T1 aligned with the x-axis, or more correctly, the x-axis aligned with T1. The y-axis has to go at right angles to that. So we will draw it in the conventional way. Now, T1 is now lying along the x-axis, which is very handy for us because that means that we would treat it just like all of the forces we've been putting along x and y axes in all of these past videos. But T2 does not point along an axis. It is pointed off in an oblique direction, which means we need to do some processing on this first before we can start applying our familiar Newton's second law. Let's take a closer look at T2. Forces are vectors. They have sizes and they have directions. In this case, look at this vector. T2 has a size of 50 newtons and it's oriented at a direction of 60 degrees. 50 newtons at an orientation of 60 degrees. What type of vector is that, or what notation is that? That is polar notation. In polar notation, the size of a vector is coupled with the orientation in degrees. Now, as you probably guessed, we don't do any of our calculations in polar, which means we have to turn this vector into rectangular first. And how do we do that? In exactly the same way that we translated it into rectangular back when we were solving for kinematics quantities. We break it into a vertical component and a horizontal component. And the equations are as follows. The horizontal component is going to be T2 times the cosine of 60 degrees. And the vertical component, because this is now the opposite side of this angle, whereas this was the adjacent side, this will become T2 sine of 60 degrees. So now what we have done is we are going to use these formulas in order to figure out the size of this force by breaking it down into x and y components. Let's take a look at what's happening in the x direction. The total force in the x direction is composed of two different forces. There's T1, which is pointed rightwards, and there's T2 cos 60 degrees, which is also pointed rightwards. Okay. So if we were to take a look at these two quantities, T1 and T2 cos 60 degrees, these two quantities put together have to be equal to mass times acceleration, because total force in the x direction is equal to mass times acceleration. So T1 plus T2 cos 60 equals ma. Now it becomes plug and chug. T1 is 50 plus 50 cos 60 degrees is equal to mass 20 times acceleration. 50 cos 60 degrees works out to 25. So we now have 50 plus 25 equals 20 times acceleration. 50 plus 25 is of course 75. So 75 is equal to 20 times acceleration. And dividing both sides by 20, you get the acceleration in the x direction, which is 75 divided by 20, which is 3.75 I hat meters per second squared. So this is the acceleration in the x direction. What about the y direction? In the y direction, the total force is equal to T2 sine 60 degrees. That's the only force which is operating in the y direction. And of course, since that is the total force in y, that must in turn be equal to mass times acceleration. Again, let's plug in what we know. T2 is also 50 times the sine of 60 degrees is equal to mass 20 times acceleration. So 50 times the sine of 60, if you were to use your calculator and work that out, that would work out to 43.3. I don't need my calculator, but then again, I'm also a nerd. So we now get 43.3 is equal to 20 times acceleration. So that means that when you solve for the acceleration by dividing both sides by 20, you're going to get let's see, 43.3 divided by 20, that would be 21, so 2.165 j hat meters per second squared. So this is the acceleration in the y direction. So putting these two pieces of information together, we can say that the overall acceleration that this asteroid is going to feel is composed of 3.75 I hat, that's its acceleration in the x direction, plus 2.165 j hat, that's its acceleration in the y direction, meters per second squared. In other words, this asteroid is going to start accelerating in a direction kind of like this. Up and, or higher than the horizontal, but not quite as high as 60 degrees. That's what this acceleration over here corresponds to. Now, let's introduce some common forces. Consider this puzzle. You pull a 20 kilogram object along the ground using a rope.
The rope is angled at 30 degrees above the horizontal. The tension in the rope is 100 newtons. There is no friction. What is the acceleration of the object?
In this case, we have been given a 20 kilogram object and it is being pulled on a rope. The angle of the rope is 30 degrees and the tension in the rope is 100 newtons. Now, let's draw the free body diagram for this object. This object is going to have the familiar weight force down and the normal force up. And the last force that it is experiencing is the tension force. Mercifully, we have been told that we can ignore friction. We've been told that the surface is frictionless. So we will start by solving out what the acceleration must be in this case. Now, in this case, we know that the axes will be drawn in a very similar way to how we've always drawn them. We can set the y-axis in our usual way and the x-axis in our usual way. And we're allowed to do this, of course, because the origin always has to be at the spot. And we like to line up our axes such that as many of the forces as possible are lying along them. So that just leaves the tension force, which is at an oblique angle. The tension force is now 100 newtons at an angle of 30 degrees. So we just need to convert this 100 newtons angle of 30 degrees from polar into Cartesian. So the horizontal component of this force would be T cos 30 degrees, and the vertical component T sine 30 degrees. Now, let us figure out what the acceleration of this object will be. Strictly speaking, we only need to solve out for what's happening in x, but to gain a full picture, let's see what's happening in y as well. In the y direction, the total force is given by three forces. There's the weight pointing down and there's the normal pointing up, but look at this. Tension now also has a component pointing up. So the total force here in y now becomes normal plus tension sine 30 degrees plus the negative weight, which is the same thing as subtracting the weight. Now, let us take this total force over here. We know that this total force must be equal to mass times acceleration. So, normal force plus T sine 30 degrees plus negative weight is equal to mass times acceleration. There is no acceleration in the y direction. This object is not collapsing into the surface, nor is it levitating from the surface. So this acceleration becomes 0, and so does the entire right side. The normal force we do not know. The tension is 100 newtons. The sine of 30 is 0.5. And then we see that we don't know the weight yet either. So let's solve for the weight. That's equal to mass times gravity, which is equal to 20 times 9.81, which is equal to 196.2. So what we have now is the normal force plus 100 times 0.5. Again, I'm a nerd. I know what sine 30 is. It's 0.5. 100 times 0.5 is 50, minus a weight of 196.2 is all equal to 0. So when you simplify this, move the 196.2 to the other side, move the 50 to the other side, you end up with the normal force is equal to 146.2 newtons. And this would be in the j hat direction. So this was the only unknown in the y direction. Now, do we notice something a little bit strange here? The fact that you had a tension which was pulling upwards on this object meant that the normal force grew smaller. The normal force is now no longer responsible for completely outdoing or countering the force of weight, because the tension is countering some of the weight as well. So the normal force grows smaller. That will become important in the next question. For now, we will just note this and we will proceed to answer the rest of the question. Now, to solve for what's happening in the x direction. In this question, there's actually only one component of one force that's pointing in the x direction, and that's t cos 30 degrees. Whenever you have forces that are at oblique angles, when you have broken them into their components, you don't deal with the original force anymore. You deal only with the components. So in x, the total force is going to be t cos 30 degrees. That's it. Now, the total force is equal to mass times acceleration, according to Newton's second law. So let's combine these two. Tension cos 30 degrees is going to give you mass times acceleration. Tension, 100. The cosine of 30 degrees happens to be 0.866. Again, I know this because I'm a nerd. Is equal to a mass, 20, times acceleration. So 100 times 0.866 will give you 86.6, is equal to 20 times the acceleration. Then divide both sides by 20, and you get the acceleration is equal to 4.33 I hat meters per second squared. So this is the acceleration. This is the acceleration that the angled string is going to produce on this 20 kilogram object.
The most amazing part of this puzzle is that the normal force decreased when a component of tension was in the vertical direction. This has major implications if friction is not zero. Have you ever noticed that if you can lift a heavy object, it suddenly becomes much easier to slide along the ground? Well, now we will explain why. Consider this situation. You pull a 20 kilogram object along the floor using a rope. You apply a force of 100 newtons. The rope is angled at 30 degrees above the horizontal. The coefficient of kinetic friction is 0.1. What is the acceleration of the object? We'll start in the usual way, by drawing a picture and then drawing the free body diagram. We'll next set our origin and axes. We immediately notice that the tension in the rope is not pointed along either axis. Instead, we see it is oriented 30 degrees above the horizontal, as was said in the question, and we know its size is 100 newtons. In other words, we have been given the size and angle of orientation of a force vector. This is polar notation. But this whole time, we've been doing our calculations in Cartesian, x and y. Before we can use the tension force, we need to convert it into Cartesian. And that's exactly what we do. The angle is expressed in the standard form, with positive x being 0 degrees and counterclockwise being the positive direction. So we apply our familiar formulas for turning a polar vector into a Cartesian one. The horizontal component is given by t cos theta, that's t cos 30 degrees, and the vertical component by t sine 30 degrees. We will use these components rather than the original vector in our calculations from here on out. Let's write out the force balance in the y direction. There are now two forces pointed up, the normal force and the vertical component of tension, T sine 30. And there's one force pointed down, weight. We can substitute these into Newton's second law. We first need to find the weight. It works out to 196.2 newtons. The object is not moving in the vertical direction, up or down, so the acceleration in y is 0. Substituting in the weight and the value of tension, the only unknown is the normal force. It works out to 146.2 newtons. Now we turn to the x direction. There are two forces in the x direction, the horizontal component of tension and kinetic friction. First, we solve for friction. 0.1 times the normal force yields 14.62 newtons. Then we substitute in the other knowns. And finally we solve for the acceleration, 3.6 I hat meters per second squared. Note that we had to solve the y direction even though there's no motion in that direction. That's because we needed the value of the normal force to find the friction force. The value of the normal force did not equal the value of the weight force. That's because the vertical component of tension is partly responsible for supporting the weight of the block, so the normal force becomes smaller. You might have noticed this yourself. If you lift an object slightly, it suddenly feels a lot easier to move along the floor. That's because that slight lift decreases the normal force, and since the friction force depends on the normal force, it decreases the friction force as well. A famous puzzle involves an object strung from the ceiling of a vehicle. The ball will hang straight downwards if the vehicle is at rest or if the velocity is constant. But if the vehicle is accelerating, the object will lean in one direction or the other. Consider this puzzle. A 0.5 kilogram ball is strung from the roof of a train car. As the train accelerates, the ball leans backward, and the string forms a 10-degree angle from the vertical. What is the acceleration of the train?
In this case, we were told that there is a train car which is accelerating. I'll draw it something like this. And as it does so, a ball, which is attached via a string to the roof of the car or to the ceiling of the car, is going to start leaning backwards like this. The angle between the string and the vertical is 10 degrees. So what we want to find out is, what is the acceleration of the car that is required to produce this lean? Let's take a look at the free body diagram. I'm going to represent the ball as this spot. Now, this ball is going to feel our familiar sense of weight, but since it's not resting on any surface, there is no normal force. The only other force it's feeling is the tension that's there in the string. Now, we are now ready to start applying our axes. I will set my vertical axis to be in line with the weight. So this will be the y direction. The origin, of course, always goes on the spot in the free body diagram. And the x-axis I will set in the conventional way, with right being positive. Now, before we go any further, before we start breaking our force into its components, there's something that is critically important but very subtle, and we must make a note of it right now. this 10 degrees, this was away from the vertical. That means that this angle was 10 degrees. Which means that this angle, the angle away from the x-axis, that's the angle that we use to decide all of our orientations, they're always done with respect to positive x, is 80 degrees. You always have to be careful where the angle is, whether it's with respect to the vertical or whether it's with respect to the horizontal. We need to break it down accordingly. So, now we're ready to perform the breakdown, or the conversion of a tension from polar coordinates with the angle of 80 degrees to Cartesian coordinates. So, the horizontal component is always given using the cosine, t cosine 80 degrees. Actually, I should be a little bit careful. I shouldn't say it's always given, but I should say it's given because this is the adjacent side of the 80 degrees. The vertical component is given as t sine of 80 degrees. Now, we have now broken or converted our force, which was originally in polar, into its Cartesian equivalent, or its rectangular equivalent. So now let's take a look at what is happening in the y direction. We'll need to do this because right now we don't have enough information about the tension in order to figure out what the acceleration is. So first we must figure out what the tension is, and only then we can figure out the acceleration. In the y direction, there are two forces acting. There is tension sine 80 degrees, which is pointed up, and the weight force pointed down. Now, the total force in this case amounts to mass times acceleration. So we can combine these two terms, or these two equations. Tension sine 80 degrees plus negative w is equal to mass times acceleration. Now, in this case, we know that the ball is accelerating horizontally, but it's not accelerating vertically. It's not speeding up going upwards, and it's not speeding up going downwards. That means that the acceleration in the vertical direction is 0. So now we have t sine 80 degrees plus the negative weight is equal to 0. How much is the weight? The weight is equal to mass times gravity. The mass of the ball was 0.5 kilograms. Gravity is 9.81. So half of 9.81, that would be 4.905. And this would be the weight, 4.905 newtons. That would be the size of the weight of the ball. So plugging that in here, we get t sine 80 degrees minus the weight, which is 4.905, equals 0. Now, the sine of 80 degrees is 0.985. So we can simplify this by saying 0.985 times the tension, and I'll move the 4.905 to the other side, it becomes positive, is equal to 4.905. Therefore, the size of the tension has got to be 4.905 divided by 0.985, which is 4.981. So the tension in the string is 4.981 newtons. And if I really want to be rigorous about it, I should say that's the size of the tension. The orientation of the tension is 80 degrees. So the full description of this tension vector would be 4.981 newtons at an orientation of 80 degrees above the horizontal. Now that we know the tension in the string, we can use that to find the acceleration of the ball and therefore the acceleration of the train car. In the x direction, the total force that's being experienced is the tension cos 80 degrees. That's the only force. Remember, once we have converted a force from polar to Cartesian, we only deal with the Cartesian parts. We never deal with the original force anymore. So it's only the sine and the cosine which become important. But, again, Newton's second law. Total force is equal to mass times acceleration. Therefore, tension times the cos of 80 degrees is equal to mass times acceleration. Now, the tension is 4.981 newtons. We calculated that just a moment ago. Times the cosine of 80 degrees is equal to the mass, 0.5, times the acceleration. So, 4.981 times the cosine of 80 degrees, that gives us 0.865. Now I just need to divide both sides by 0.5, and that gives me the acceleration. 1.73. So the acceleration of the ball and the acceleration of the train car would be 1.73 I hat meters per second squared.
Another question involves an object on two uneven strings. The tensions will obviously be unequal. Consider this puzzle. A 2 kilogram object is supported by two strings. The left string is angled 20 degrees below the horizontal and the right string 30 degrees below the horizontal. The object does not move. What are the tensions in the strings?
We start by drawing a picture. Here's the ceiling, and here is our object being suspended from two ropes, like that. Now, let us say that this rope on the left has a tension T1 and the rope on the right has a tension T2. The tensions are the two things that are unknown in this question, so that's what we're solving for. But as you probably guessed, if we have two unknowns, that means we're going to need two equations to solve. Now, we were told that the left string is oriented at 20 degrees below the horizontal, and that means that this angle must also be 20 degrees. Likewise, the right string is oriented at 30 degrees below the horizontal, which means that this angle must also be 30 degrees. These two angles down here we get from geometry, and the reason why they are important is because when we ultimately solve out for the orientations of these tensions, they're going to be done with respect to this object. So we'll have one tension pointed this way, one tension pointed this way, and the orientations will be based off of these angles down here. Now, let us draw out the free body diagram. I have this spot over here, which is going to stand for our 2 kilogram object. There is the usual weight pointed down, but there's also tension 2 pointed off in this direction, and there's tension 1 pointed off in this direction. Now, we are ready to draw our axes. The origin obviously goes on the spot, as it always does. I'm going to set our axes in the conventional way. This way is x, this way is y. So this tension over here was oriented at 30 degrees. This tension over here is oriented at 20 degrees, but we have to be careful. It's 20 degrees above the negative x-axis, which means that its real orientation is 160 degrees. That's 180 minus that. Now, we are now ready to break these forces, these two tensions, down into their Cartesian or rectangular equivalents. We now have T1, which has an angle of 160 degrees, and T2, which has an angle of 30 degrees. So let's start by breaking T2 down. This is the adjacent side of 30 degrees. That means that it's going to have a cosine attached to it. T2 cos 30 degrees. What about this? This is the opposite side. So this is going to be T2 sine of 30 degrees. What about for T1? It can be broken down into its rectangular coordinates as well. So this horizontal part is going to be T1 cos 160 degrees. And this vertical part is going to be T1 sine of 160 degrees. Now we have broken down both of these oblique forces into their Cartesian or rectangular coordinates. So the next step is to evaluate what is taking place along the x-axis and evaluate what's taking place along the y-axis. The original forces of T2 and T1 do not play a role anymore. Only their components do. In the x direction, the total force is given by this rightward component, which is T2 cos 30 degrees, plus the leftward component, T1 cos 160 degrees. Cos 160 happens to be negative, so basically this is going to turn into a subtraction. Now the total force is equal to mass times acceleration. So T2 cos 30 degrees plus T1 cos 160 degrees equals mass times acceleration. Now, the object over here isn't accelerating, it isn't even moving. So that means that acceleration is 0. And the entire right side goes to 0 as well. The cos of 30 degrees is 0.866. The cos of 160 degrees is negative 0.94. That's equal to 0. Now, this negative term I'm going to move to the other side. 0.866 times T2 is equal to 0.94 times T1. So 0.94 divided by 0.866 works out to 1.085. So I could say now that T2 is equal to 1.085 times T1. This is the first relationship that I have between these two forces. Remember what I said earlier. Because there are two unknowns, we're going to need two equations. This is the first of them. We'll turn to the y direction to solve for the second one. Now let's take a look at everything that's happening in the y direction. The sum of the forces here now includes three forces. There is the vertical component of the first tension, plus the vertical component of the second tension, plus the negative weight, which is pointing downwards. And all of that's equal, and all of that is going to equal mass times acceleration. Now, we could start simplifying this a little bit. I'm going to combine them first. So we now have T1 sine 160 degrees plus T2 sine 30 degrees plus negative absolute value of W equals mass times acceleration. Now, we know again that this object is not moving, so that means that its acceleration in the x direction is 0. What about its weight? Its weight is given by mass times gravity, which is mass 2 times gravity, 9.81, which is equal to 19.62. So, T1 times, now let's start solving for some of these trigonometric quantities. The sine of 160 degrees is 0.342. Plus T2, sine of 30 degrees I happen to know is equal to 0.5, minus 19.62 equals 0. So simplifying this, we now have 0.342 T1 plus 0.5. Now, what do we know that T2 is equal to? Well, a moment ago we figured out that T2 was equal to 1.085 times T1. We had worked that out from the horizontal components. And all of that is equal to 19.62. So, 0.5 times 1.085 plus 0.342 gives us 0.8845. So we end up with, really should get these to stick better, you know that? 0.8845 times T1 is equal to 19.62. Divide both sides by 0.8845 and we get 22.18. That is the size of T1. Finally, going back to where we started from, since we know that T2 is equal to 1.085 times T1, that means that T2 equals 1.085 times T1, which was 22.18, which is 24.07. This then is the size of T2.
We can expand the concepts we've seen to more complex cases. Consider this situation. Two tugboats pull a 1,000 kilogram object using ropes. The object accelerates at 0.1 meters per second squared eastwards. One tugboat pulls with a force of 500 newtons oriented at an angle of 10 degrees north of east. The force of friction is 600 newtons. What is the strength and direction of the second tugboat's pull? We start by drawing a picture. Logically, if the overall pull is eastwards and one pull is north of east, the other pull must be south of east. Next, we draw a free body diagram and set origin and axes. There are two tensions, both at oblique angles. Kinetic friction is always opposite the direction of motion, so it points west. Before we can proceed, we must break the tensions into their respective components. The first is easy to do. We just use T1 cos 10 degrees for x and T1 sine 10 degrees for y. But the size and angle of the second tension are both unknown. We will call them T2 cos theta in x and T2 sine theta in y. Next, we set up the force balance in the y direction. The total force is T1 sine 10 degrees minus T2 sine theta. We can substitute the known information. There's no motion in the y direction, so the acceleration is 0. Simplifying, we get T2 sine theta equals negative 86.82 j hat newtons. Note that there are two unknowns here. We cannot solve further without information in x. In the x direction, the force balance contains T1 cos 10 degrees plus T2 cos theta minus kinetic friction. Applying Newton's second law, all of that is equal to mass times acceleration. Plugging in the known information and simplifying, we get T2 cos theta equals 207.6 I hat newtons. Now, back in the y direction, we got T2 sine theta equals negative 86.82 j hat newtons. If we were to divide the expression from the y direction by the expression in the x direction, the T2's would cancel out, and we would be left with sine theta over cos theta. But we can now apply a trigonometric identity. Sine theta over cos theta equals tan theta. So we end up with tan theta equals negative 0.418, and taking the arctangent of that, we get theta equals negative 22.7 degrees. And since we earlier said that T2 sine theta must equal negative 86.82 j hat newtons, we can work out that the strength of T2 is 225 newtons. In this video, we explored friction and saw more complex examples of force balances. In the next two videos, we will see more applications of Newton's second law.